Okay, guys, let's start. Let's start solving some questions about our lessons. So we're going to start with the first homework. The, this one, but I need to share it from the Zoom itself to be able to date it. Okay, let's go. This sheet was about Kepler first law. What force holds Earth in orbit around the Sun? The force is gravitational force. So we can write here gravitational force. What is the shape of Earth's orbit? Earth's orbit, the shape is the ellipse shape. What is the sun located? Where is the sun located relative to the Earth? Sun located at one of the centers of the ellipse shape. Ellipse shape has two centers. Sun is located at one center of these centers. At which point in its orbit around the sun does the Earth move fastest? We said before, as Earth moves near the sun, it's going to move faster to escape from the sun gravitational force or sun gravity. So as the radius decreases, the speed of the planet or the Earth itself is going to increase. Here is the shortest here. Just a minute. Here is the shortest radius. So in this period, I think that sun going to move fast as the time is equal, of the interval of times are equal. So we're going to cover a larger distance with a larger speed. We know that v equal distance over time. So the time is constant, v directly proportional with distance. So the largest distance is here. So also the largest velocity is here. This interval, this part. And the next question. At which point in its orbit does Earth move slowest? The farthest point is here. So we can consider this point. At this point, the speed here or here. At this point, this one or this one. This point is represent the farthest point from the sun, so the lowest gravity and low speed. Low speed, so the lowest distance covered. This part going to be applied as the answer of the last question. If T1 equal T2, how do areas 1 and 2 compare? Areas are equal to each other. We said this equal to this represented by Kepler second law. Kepler second law mentions that for equal times, equal areas swept or covered from the sun at equal intervals of time as the distance and speed of the rotation, the revolving of the sun differ from one position to another according to the difference in gravity. Next question. If area 1 and area 2, area 1 equal to area 2, how do T1 and T2 compare? We said it before. Velocity change by changing the gravitational force. to provide equal distance covered, equal areas covered from the sun. So we're done with the first homework. Let's see the second one. Here's the second homework. Yes. Need to second homework. Pay attention about while solving it. It's a long homework, so you have to pay attention. Do it correctly also. First question. According to multiple choice, non-MCQ questions, according to Kepler's first law, the path of the planet follows around the sun is an ellipse path. Answer B. Kepler's first law states that the sun is located at one center. No explanation is required here. Newton's found that the gravitational force between two masses is inversely proportional to the square of. Here we have to write. And you have to also to learn. You have to learn how to find the relation through the law itself. The law here is Fg equal G, gravitational constant 6.6 times 6.67 times 10 to the power negative 11. It's a constant. Mass 1 multiplied by mass 2 divided by r squared. So the answer is Fg is inversely proportional to the square of the distance. Proportional to the square of the distance between them. And he mentioned here the word square. Next question. Number 4. Increase in the strength of the gravitational field surrounding an orbit result from an mass. As the mass increase, the object gravitational force of gravity also increase. A gravitational field surround anything has a gravitational field surround anything that has density of gravitational field. As you move towards the object itself, the density of the field increase. You move away from the object, so the density of the object decrease. Okay. The gravitational force between two masses is inversely here. We are here. The speed of satellite orbiting Earth is directly proportional to the speed. The value, the rule of the speed. I'm able to write. V equal square root of G M over R. M represents the mass of the object which exists at the center of rotation. So the speed of satellite is proportional to the mass of the object at the center. We are talking about satellite revolving around the Earth, so we can put here mass of Earth. Mass of Earth. Earth here. E. The speed of satellite orbiting Earth is proportional to Earth's masses. Yes, Earth's masses. The satellite mass, no satellite mass is not included. The mass of the object which revolves around another one is not included in calculating its velocity. The square root of the Earth's mass or the square root of the satellite mass. Sorry, guys. It's the square root. The square root of the Earth's mass. Okay. Next one, gravitational force between two masses is inversely proportional to the gravitational force Fg. We know this before. Fg is equal G M1 M2 over r square is the most linear square of the distance between them. So it's the same question here. Okay. The square of planet's period is directly proportional to the cube of its Kepler's third law. Kepler's third law says that T1 over T2 or TA over TB squared equal R1 over R2 A over B cubed. So the square of the time period, the periodic time, is directly proportional to the cube of the distance between objects. So what's the question? The square of the planet's is directly proportional to the cube of its uh, radius, orbital radius. The next question. طيب, let's start these questions, guys, starting from question number 9. An object is a mass experience force when placed in a rotational field of another object. An object resistance to acceleration is determined by its friction just of acceleration or motion. Amount of force an object exerts on another object is determined by its mass. Um, according to the rule of gravitational force, the object gravitational mass and inertial mass are equal. A satellite is in A when moving above Earth in equilibrium. Equilibrium is centripetal force equals centrifugal force. On Earth's surface, a gravitational field أو acceleration of gravity is equal to 9.8 per kilogram. Number 15 is cancelled. We're not going to answer it because I cancel the part of Einstein's theory. Question number 16. For each statement below, write or rewrite it horizontal bird machine. Kepler's first law states that the planet moves in a circular orbit, not a singular orbit, an ellipse orbit, with the sun at the center, at one center of them. Kepler's second law states that an imaginary line from the sun to a planet swept out equal areas in equal time. That's true. Kepler's third law says that the square of the ratio of the period of any two planets is equal to the cube of the ratio of the distance from each other, not from each other, from the sun. Number 19, the strength of gravitational field depends on the mass of the object experiencing it. The strength of the gravitational field depends on the mass of not experiencing it. It's the object at the center. It's the object at the center. Applying it, not experiencing it. The apparent weightlessness astronauts experience is due to lack of gravity when in orbit around Earth. Not the lack of gravity, it's the lack of contact force. Question 21. A satellite orbital speed and period are independent of satellite mass forces. They are dependent on the object at the center, which is the Earth. A gravitational field point where is the center of the object that created the field. That's true. Question number 23 and question number 24 are cancelled. Critical thinking question. What made Tycho this question is cancelled. It's for research. Explain how Kepler's third law of a planetary motion supports the idea that all planets orbit the sun rather than orbit Earth. Because the sun is exactly at the center and it applies a field of gravity, or it's the object with the greatest mass. So all of the orbital or all of the planetary orbit the sun, which exists at the center, and the radius of uh, orbit, each orbit is directly proportional to the time or periodic time of the motion. Examine the graph below, which of the four lines most accurately represents the relation between the gravitational force and distance. Why did you eliminate the other three? Okay. Slope number E. Represent inverse, inverse, uh, inverse, and changing relation. Number D. Represent inverse and constant relation. Number C. Represent direct and constant relation. Number B is remained, represent direct and changing relation, not constant. The ratio change from one moment to another. Okay. He asking about relation between the gravitational force and the distance. Gravitational force and the distance. So we have to return back. Gravitational force, Fg, and the distance. So Fg equal G m1 m2 divided by r squared. Fg and the distance between the two objects. Here's the relation between Fg and the square of r. First of all, it's inverse relation. Inverse relation. So we have to eliminate C and D. The relation between Fg and r squared, not Fg and r. So it's a changing relation, not a constant relation. So we're going to choose A, slope number A. The next question. Examine the graph in question 3. Which of the lines correctly describe the relation between gravitational force and mass? Gravitational force and mass, Fg equal G m1 m2. He said mass, not masses. So I'm going to choose C as Fg equal G m1 m2. So it has a direct relation with each mass of each planet or object individually. We're going to find the product of the masses, it will be E. But actually, he's asking about the mass. So you're going to find each one individually. You're going to find each one individually. Okay. Here, question number, I'm going to solve one only because they have the same rule. And you have to solve the rest. And already you have the answers of this question, by the way. He need, for this table, he need number 5, number 6, number 7. Number 5 represents the distance from sun in kilometer. And so he needs the distance twice, the distance with different two planets, Mercury and Venus. And also he needs the periodic time of Mars. We are going to use one rule, which is Kepler's third rule. Kepler's third rule is T1 or TA over TB squared equal RA over RB cubed. Choose, we are going to solve for mercury by mercury with A. So we have here RA mass, TA given. Have to lose another planet with complete data. So we're going to choose Earth. Earth has distance, also has period. Distance here is RB and TB. Substitute in this question and find the answer. The substitution will be as following. TA is 88 divided by 365.2, all of this one squared, equal RA, which is mass, divided by 1.5 times 10 to the power 8, 10 to the power 8, cubed. By putting this relation in the calculator to find that, or we can do it manually. Let's do it manually. يبقى 8 over 365.2 times 1.5 times 10 to the power 8 cubed. All of this under the cubic root, صح كده؟ cubic root to present RA. And so the final answer will be the answer will be 5.81 times 10 to the power 7 kilometer. For the next question, number 9, describe the relation between the strength of Earth's gravitational field and the distance from the center of the Earth. Okay, guys. Sorry, I missed this question. If the universal gravitational constant was discovered to be larger than the currently accepted value, what impact would that have on Earth's mass? Let's say that for gravitational constant, Fg is equal G m1 m2 over r squared. One of them is the mass of Earth, and the other one is the mass of Sun. Let's say that this one is Earth and this one is Sun. So, if the value of G increase, the value of M must decrease if we're going to have the same gravitational force. So, if you have a constant gravitational force, that means the mass of the Earth will decrease or the mass of the Sun will decrease to have the same amount of attraction, the same amount of gravitational force. If we're going to have different value of gravitational force, as it's going to be larger, the mass of the Earth and the mass of the Sun are going to stay the same. For next question, describe the relation between the strength of Earth's gravitational field and the distance from the Sun. Shows gravitational field can be measured G equal GME over R square. Gravitational field of the Earth depend on the mass of the Earth itself, and it has a direct relation. And it has also an inverse relation with the square of the distance between the object and the Earth's surface, or the core of the Earth itself. Let's say the core of the Earth, as R represents the distance from the core of the Earth towards the Earth's crust, then the height from the object from the Earth's crust. Here is RE, here is H, and R is the summation of RE plus H. So the relation between them is an inverse relation. As the distance increases, the gravitational field decreases, and the relation is not constant and represented by a square. So small change in the distance make a huge change in the difference in the gravitational field. What would happen to the strength? We have 2 minutes to answer. What would happen to the strength of the gravitational field on Earth using the same rule? You can read the question using the same rule. The rule is saying that G equal G M E over R square. So the relation between R and E is inverse relation. Halved. The radius is going to be halved. This means R new R going to equal, going to call it R star, equal half R, the old one. Substitute, the rule will be G M E over R star. Squared. So G M E over half R squared. So it will be going to solve here, complete here. Mu G equal mu G star, mu G. This one also is star, mu G. G equal G M E quarter R square. This one represents the old G. So G star will be, quarter would be inversed as denominator of denominator. It will be denominator, so it will be 4. G M E. M E is one symbol represents the mass of the Earth, and over R square. So it will be multiplied by 4. The new one will be multiplied by 4 as the radius decrease to the half its value. Question number 10. We already answered that. Earth's mass is far larger than either of the lead sphere. In experiment, this one is cancelled, number 11 is cancelled, and number 12 also I cancelled this experiment. Number 13, explain how the general theory of relativity also cancelled. So going directly to question number 1. Okay, a planet is discovered and found to have a circular orbit. How is the planet, or how is this planet's gravitational interaction with the sun different from of the Earth? The Earth moves in a circular, in an ellipse orbital. Moving in an ellipse orbital makes the gravity or gravitational force differ from one location to another according to the distance from different distance from the sun. For a circular orbit, this planet going to move in a circular orbit, so it's going to have the same distance, the same radius each moment. So the gravitational field applied on this planet going to be constant, and it's going to provide also a type of, let's say that, a constant speed of rotation, revolving around the sun. So this planet going to have a constant gravitational force between the planet and the sun, and also going to have a constant gravitational force applied. Recall that the satellite speed is calculated using the formula V square root of GME over R. If the Earth is closer, I need to write that. If the Earth is closer in December, if the Earth is closer in December than in July, which month is Earth moving faster؟ يبقى الدستنس closer يعني الدستنس in December less than what in July. I'm trying to fix it. Easier. The distance in December is less than the distance in July. So, as the distance decreases, the gravitational force increases. As the distance R, make it R decrease, Fg increase. As Fg increase, the planet itself need to increase its velocity to escape from the gravitational force. So the Earth is faster. The Earth is faster in December. In which month Earth moving faster? In December. And we can write the rule of velocity equal square root of GME over R. So it has an inverse relation with R. Next question, explore. We can calculate the period of time by using two rules. One of them is the Kepler third rule, which is T1 over T2 squared equal R1 over R2 cubed, and T here represent the periodic time. And also we have another one, which is T equal 2 by the square root of GM S. I'm talking about the planet MS over R cubed. Sorry, I reversed it. R cubed over GMS. I'm sorry, I reversed it. How did I know that I reversed it? R cubed over GM the sun, because I know that the relation between time and R is directly proportional. So I checked it rapidly. I found that I made an opposite relation, an inverse relation. The surface gravity on Jupiter. Okay, the surface gravity of Jupiter is less than 3 times of Earth. Yeah, and it's less than maybe 2.5, 2.7 of the Earth. Let's annotate to draw and explain it. Jupiter is less than 3 times. Less than 3 times mean 2.7, say 2.8, something like that, the gravity of the Earth. While it's 318 of its mass. In Jupiter, as the mass increases, the size and the volume of the planet itself increase. And we know that, guys. Fg is equal Gm1 to, let's say, Jupiter and Sun over R square. The increase in the radius of Jupiter as the volume increase make a huge difference for the gravitational force, and this huge difference is greater than the one which made by the mass itself. The mass is directly proportional to the force of gravity of the same power. So it's going to increase by 1, the force of gravity is going to increase by 1. They're going to increase by 10, the force of gravity, the mass increase by 10, the force of gravity also going to increase by 10. So it's related in the same ratio. The force of gravity is inversely proportional to the square of the radius. It's going to increase, the radius is going to increase only by 2 times. The force of gravity will decrease to the fourth its value, 1/4 its value. It means to 4 times, the force of gravity is going to decrease to 1/16 of its value. It's going to increase 10 times, tenths of the value, hundredths its value. So the relation not with the radius itself, the relation is the square of the radius. So going to square the change and make the difference. Okay, I think you got it now. So 318 more than massive, the mass multiplied here by 3.18. 318, but the radius increased how many times, and these times must be squared. So going to overcome the increase, the huge increase in the mass. So in Jupiter, as the mass increase, it's not be a massive object, the mass increase in a small volume to make the density increase. No, the mass increase and the volume of the Jupiter itself increase. Question number 5. Question number 5 is cancelled. Question, I need to remove the page. Okay, stop annotation. We have some problems to solve, and we're done. Okay. Let's see the solution of these problems. Number 1. I'm going to explain what I solved already. Stop sharing. Share. Okay, I'm going to explain what I solved already. For the first question was saying that Earth is 1.5 times 10 to the power 11 meter from the sun and has a period of 365.2 days. Mars is an average of 2.28 times 10 to the power 11 meter from the sun. What is the orbital period of Mars in Earth year? Let's see the answer. First of all, you have to find the governance. Radius of the Earth is 1.5 times 10 to the power 11 meter. Time of Earth is 365.2 days. Radius of Mars is 2.28 times 10 to the power 11. He needs the period, the time of Mars. I'm going to use Kepler's third law, substitute the values, then find the time of Mars in days. You need to convert it into years, so you're going to divide by 365.2 days to convert into years. It will be 1.87 year of Earth. Question number 7. Question number 7. Two spheres 1.02 kilometer apart. One of the spheres has a mass of 57 kilogram, and the gravitational force between the spheres is Fg is 10 of 1.79 times 10 of power negative 14 Newton. Find the mass of other sphere. He's using here the force of the rule of force of gravity, gravitational force. The given, we got the given, but notice that the radius is presented in kilometer. You have to change it into meter, so multiplied by 1,000. Substituting or finding the m FGR square divided by m1g, and substitute, going to find the mass of the second object. He needs number 8. A planet orbits Sun radius 2.7 times 10 to the power 9 kilometer. If the mass of the Sun is, he needs the periodic time of the planet. And this question, you have a given radius 2.87 times 10 to the power 9 kilometer. You have to change it into meter by multiplying in 1,000. So the answer will be 2.87 times 10 to the power 12. The mass of the Sun, 1.99 times 10 to the power 30 kilogram. Going to substitute in the rule of periodic time, T equal 2 by square root of R cubed GMS. Substitute to find the answer. The answer is 2.6516 times 10 to the power 9, and you have to convert it, if you like, to the Earth year, which is 980, I think 84. Okay, find the velocity for the same example. The last question, you're going to start using the same data to substitute in velocity and find the velocity. To convert from meter per second to kilometer per hour, you have to divide by 3.6. So we have the figure in meter per second, and also we have it in kilometer per hour. Let's go for the next sheet. Okay, we're done with questions. There's no more sheets. There is no more questions. Okay, guys, study well and good luck. See you.